This podcast is sponsored by AppDynamics, a leader in business and application performance monitoring. Optimize app performance, increase team velocity, and drive business with end-to-end visibility, from code level to customer experience.
Welcome to the InfoQ podcast, a software engineering podcast brought to you by the people behind InfoQ.com and the global QCon software conferences. I'm Charles Humble, InfoQ's editor-in-chief, and today I'm talking to Sylvan Clebsch, who is the designer of the Pony programming language and now works at Microsoft Research in Cambridge in the Programming Language Principles group. Sylvan, welcome to the InfoQ podcast.
Thank you.
So maybe you could start by giving us a bit of your background. Obviously, Microsoft Research is kind of academic and you've spent quite a lot of time. You were at Imperial when you were working on Pony, I know, but you've also done quite a lot of work in industry as well, I think, right?
That's right, yeah. So I've been an industry programmer for about 25 years, and I've covered a sort of an interesting mix, maybe, or possibly just interesting to me, of various projects, ranging from embedded operating systems, cryptographic systems, VoIP, back when that was interesting, video games, and of course, fintech. I worked at an investment bank for some time running European electronic trading infrastructure before finally going and working on Pony and then coming here to MSR. So, I've been working on various industry problems for a while. I suppose the thing that I often say about this stuff is that it turns out those were all a lot more similar than I thought they were when I was working on them, which is that they all turned out to be distributed systems, even though I probably didn't know that when I was writing them.
Okay, that's really interesting. So the fact that they were distributed, was that kind of your motivation for designing Pony the way it was designed?
Yeah, definitely. Pony was designed to have the same operational semantics, that is, the same very low-level semantics of the language, whether it's running in a concurrent context or a distributed context. It's important to give a vaporware warning here, which is that Pony is useful right now for concurrent computing, but the distributed runtime is not available yet. So it's still being worked on. So I don't want to get people too excited about that. But yeah, it made a big difference. And funnily enough, for concurrent Pony, making it the same operationally as distributed Pony turned out to actually be a performance advantage rather than a performance cost, which was quite fun.
So that's quite surprising to me. What is it that causes that? How do you get the performance wins?
It's surprised the hell out of me too. It really came from thinking about garbage collection and thinking about garbage collection as something that can't involve coordination across units. Because what if those units are running on distributed computers? And if you're going to do coordinated garbage collection, if you're going to have some kind of stop the world phase or anything like that, even two-way message passing in order to do garbage collection, you're going to run into real problems. So we designed a garbage collector for Pony that is non-coordinating. It does one unidirectional message passing as part of garbage collection, but every actor can independently garbage collect without coordinating with any other actor. So it has no stop the world phase at all. And that was designed to make it amenable to distributed computing, but it turns out it's a big win for concurrent computing. It means that we just don't have those kind of garbage collection pauses that you sometimes see with other GCs.
And that's, so the GC, okay, actors collect their own heaps, which is straightforward enough, but you can also share pointers across actors, as I understand it, right?
Yeah, exactly. So in Erlang, actors collect their own heaps too, but to make that possible, messages are copied on send, and it means that sending involves copying fair amounts of data. And because I'm sort of absurdly obsessed with low-level performance, what I really wanted was zero-copy message passing all the way through, from the network stack to the actors themselves, the whole thing. So yeah, the garbage collector allows zero-copy message passing. You can basically pass pointers between actors and still have no stop-the-world GC.
I'm slightly lost there. What is it that you're actually doing that makes that work?
Yeah, good question. There's going to be it turns out there was a paper at iCoolps in 2015, and we're going to have a paper at UPSLA coming up that describes this garbage collection protocol, which is called ORCA, Object Reference Counting for Actors. It says reference counting in the title, but I almost feel like we shouldn't have done that because people get the wrong idea and they think we're doing reference counting where the shape of the heap matters and where if something points to something else, it has to increment its reference count. But that's not what we're doing. It's a protocol that has to do with a reference count that is an over-approximation based on the number of times the object has been sent or received. Actually, how about a short walkthrough of a three-person example? Does that sound good?
Yeah, that sounds fantastic.
Okay, so let's say I allocate an object. So I allocate this lovely object, and I send it to you. Now, what I'm going to do is I'm going to increment my local reference count for that thing by 1. I've sent it in a message once, and you receive it, and so because it doesn't belong to you, you increment its foreign reference count that you hold by 1. Neither of those reference counts are inside the object. Rather, they are my view of that object and your view of that object. So these aren't atomic reference counts. They're just simple operations. At that point, you can have 30,000 different things in your working set pointing to that object, and it doesn't matter. Its foreign reference count stays 1. We're not ever going to mutate that reference count while you're executing, only on send and receive. And if you drop your reference to that object, eventually you'll do GC, discover it's not in your working set, but that you have a foreign reference count of 1. So you'll say, oh, let me find the owner for that object. Oh, it's Sylvan. I'll send him a decrement of 1 for that object. I get that back. I know that there's no longer, I can lower my local reference count by 1. And hey, it's 0. If I'm not referencing it, I can collect it. That's cool. But where this becomes interesting is in a third party. Let's say I send you that object, you receive it, and you send it to Rob. And Rob goes, great, I get an object, and I'm going to increment its foreign reference count by 1. Now we have a problem. You have a foreign reference count of 1, Rob has a foreign reference count of 1, and I have a local reference count of 1. So that's not good. So instead what you do is when you want to send it to Rob, and you have a foreign reference count of only 1, you invent some references for it. You say, let's invent another 1,024 references, just because. And you send me a message that says, I've invented 1,024 references for this object. But you don't wait for a reply. You just go, that'll all work out. Everything's fine. You add that to your foreign reference count. Now you have 1,025. Now you can safely decrement that by 1 and send the object to Rob. And Rob receives it, increments it by 1. Fantastic. The really tricksy part about this is the fact that you didn't have to wait for me to respond. And the reason for that is that the Pony runtime at 0 runtime cost enforces message causality, which means that every sender-receive that you do before you send a message is a cause of that message. And classic Einsteinian light cones, those causes all have to get processed before their effects, right? We don't violate the laws of causality in this house, young lady. So you get to be absolutely certain that if Rob sends me a decrement message for the reference count that he holds, that I will have received your increment before his decrement.
Got it. Yep. That's very smart.
It's pretty fun. Now, if anyone's interested, the OOPSLA paper is really good, and it's really good because a bunch of really smart people that aren't me worked on it. But Juliana Franco and Sofia Drosopoulou and Jan Vitek and Tobias Rigstad, brilliant people. I hope when it comes out, people have a glance. It's a really nice, in-depth explanation of the protocol and all kinds of interesting edge cases around it that get handled, and it works. It's really fun.
So something else that I thought was really fascinating about Pony was the fact that you have essentially a formal proof of a type system. So you develop the type system and the runtime in parallel. Can you talk a bit about that whole process and how that works? Again, I know there's a paper supporting that, but...
Yeah. So in fact, now there's a paper and also George Steed's master's thesis supporting that. And in fact, Paul Lytard just finished off his thesis at Imperial, which extends this further. The idea is that co-designing, slight digression, but are you familiar with the term of co-design from architecture?
Yep.
Okay, so it's a bit crazy Swedish and wild, but I adore it. And it's about, making sure that the architect and the end user are both part of the design process. And so Pony is a co-designed language. It's about the type system and the runtime, both being first-class citizens. So the type system in Pony is data race free. It uses this thing called reference capabilities, which says it's a type annotation, a type qualifier, where you can start talking about isolation and immutability and opaqueness. And basically it gives you a way of saying, sure, this object has these methods on it, but this alias to this object, this reference to this object, can only call these methods. And it gives you all kinds of fun properties like isolation and immutability. And what it means is that because the entire type system is data race free, you can just never have a data race in Pony. The runtime gets to cheat like crazy and just not handle all kinds of cases that would otherwise come up. And the garbage collector is probably the primary beneficiary of this, although literally every single aspect of the runtime is influenced by the type system. But the classic example in the garbage collector is that I can safely go through and trace any object I have a reference to, regardless of who owns it, knowing that while I'm tracing it, it cannot possibly be modified by another actor. So there are never races during garbage collection. And that's pretty neat and drastically simplifies the runtime in some senses.
Do you think that sort of formal verification systems of one kind or another, sort of TLA plus those kind of things, seem to have been coming forever and for various reasons as still coming? Do you think that's kind of where we need to go with languages ultimately?
That's a fabulous question. So I think there's two really different things happening. One is proofs of things about languages, and the other is proofs about programs written in those languages. And I think we've done a really good job of moving more and more towards languages that have proofs about the language themselves. Pony is an example of that, but there are other examples too. Rust, for example, and things that people have proved all kinds of interesting things about. Haskell and about Erlang, and really interesting work has been done. Proving things about programs using approaches like Daphne or F-star or Idris or Agda, Coq, Isabel, these kinds of tools is hard. And scaling that out to full-size programs is hard. TLA Plus is really interesting because it's model checking rather than a complete proof. And it's allowed proving really interesting model checking really interesting things about distributed systems that otherwise wouldn't be possible. And it's very powerful. But it's also a bit limited. There's a really interesting project called Iron Fleet, which uses a combination of, I'm probably getting some of this wrong, this is not my research at all, but it uses a combination of Daphne and TLA Plus to provide really interesting proofs about distributed systems. And it's incredible what it can do, and yet not easy to use at all. So this is a very long-winded and crappy answer to the question. And really what it boils down to is, I think, yes, that is where we need to go. We need to be more and more responsible as software engineers about the products that we're designing, the products we're shipping, because people's lives depend on them. And traditionally we've said that, that's true in like airplanes and automobiles, and maybe, medical software, but nowhere else. But more and more it's becoming true across the board. When we ship out new machine learning tools, people's lives really can depend on them. And that's both powerful and transformative and utterly terrifying. But the other side of that is that in order to do that, we're going to need better and better proof systems, which certainly work is being done, but not fast enough, as you say. They've been the next big thing for 40 years, 50 years.
Yep.
And it's like fusion. They're the technology of tomorrow and always will be.
Yes.
On the other hand, I'm a wide-eyed optimist. I hope in my lifetime we have everything's run by fusion. We formally verify all our programs. I think we can do it. But I think one of the key things we're going to need to do is bring proofs about languages into the conversation about proofs about programs more and more. To say that languages need to be very strict about the language itself having interesting proofs and interesting type system guarantees that limit what the program proof system has to prove. So, for example, with a data race-free type system, there are lots of things you no longer have to prove about your program. You can start treating functions in isolation. If you have referential transparency in a data race-free type system, you can prove functions entirely independently and not worry about concurrency. Reducing the scope like that is pretty powerful if you have composable proofs. Don't get me wrong, we're not there yet, but I'm optimistic, I guess.
Very cool. So I'm going to sort of go up a level again. How does the actor scheduler in Pony, how is that implemented? How does that work?
Oh, great. I love this stuff. Queues. It's all about queues. Pony has two different queue implementations. One's a multi-producer single consumer queue, and that's the actor's queue of messages so that anyone can post a message to the actor. And it's got another queue, which is a single producer multi-consumer queue, which is a bit of an unusual queue. And that's how schedulers are implemented. The scheduler is implemented. So in the Pony runtime, schedulers are pinned to cores. And typically you have a scheduler per core or possibly per logical core, depending on how your program performs under hyperthreading, right? If memory pipelining is helpful or not helpful, essentially. And each of those cores is running a single scheduler thread that has a single producer multi-consumer queue. And your main actor starts up and gets scheduled on one of these things. and goes and executes its initial message, and it'll start spawning other actors and sending messages to those actors. When an actor is sent a message, the pony runtime can determine at no extra cost whether the queue of that actor was empty at the moment that that message was sent. And if so, that actor needs to be scheduled. That means it's not on any scheduler queue anywhere. So that's the sort of the decision point. Is it on a scheduler queue or is it not? If it is, we leave the actor where it is and do nothing, because cache locality for the actor's working set is likely to be more important than cache locality for the message. So we're okay with the message being handled by whatever thread the actor happens to be handled on, because performance is likely to be better because the working set is more likely to be in cache at the destination. But if the actor isn't scheduled anywhere, then it's unlikely that its working set is in cache. So we schedule that actor on the queue of the thread that sent the message, so that the cache locality for the message is likely to be the thing that's of most benefit to us. And that's why it's single producer. So any given scheduler thread only schedules actors on its own queue. But the fun part is, what does a scheduler thread do when there are no actors on its queue? And that's why it's a multi-consumer queue, is that it will pick a victim. It just round robins. It turns out we've experimented with a zillion different approaches, and round robining, even in the presence of a NUMA, we can't beat at this point. Anyway, it round robins to the other scheduler threads and steals work. It goes and steals an actor off that and says, I'll have that, and goes and processes it. This is great when there's more work to do than there are scheduler threads. But as soon as you have less work to do than there are scheduler threads, that is where it's impossible to actually do full core utilization. Currently, the Pony runtime has a really unfortunate behavior, which is these scheduler threads will go and try and steal work that should stay where it is. This is annoying. I'm working on it.
So I was surprised when I first looked at Pony that the message queues which the actors use to pass around objects are unbounded.
Yeah.
Why was that decision reached? That seemed very odd to me when I looked at it.
Yeah, you're not alone. There are a collection of reasons for this, starting from the purely theoretical to the incredibly practical. But I'll start with the thing that I think is most important, which is Gulag's PhD thesis on the actor model, where he laid out the original rules. It was written a good 10, 11, 12 years after Carl Hewitt first proposed the actor model in 1973. But Gulag's PhD thesis is and remains and probably will remain most beautiful expression of exactly what it is. And he has three rules. An actor can create other actors. It can send a finite number of messages to other actors, including itself. And it can select what behavior it will perform when it processes the next message it receives. And that's it. That's all an actor can do. The third one is just an extraordinarily elegant way of saying that an actor can keep state, right? It just means, hey, if we can select what we're going to do in the next time, well, doesn't that mean that we could have an arbitrary working set, an object graph, and we could mutate it, and then when we got the next message, we could, yeah, of course, that's exactly what it means. That's pretty cool. And the first one is pretty straightforward. It says we can create actors. That means we have a dynamic topology. That's awesome. That's one of the core differences between this and between the actor model and some other approaches. But that second one, you can send a finite number of messages to other actors, including yourself. It doesn't say you can send messages maybe. It says you can send messages. In fact, guaranteed delivery, not in any given order, but guaranteed delivery is a core part of the actor model as well. It means when you send a message, the recipient will receive it someday, maybe in 1,000 years, but they will receive it, which is unbounded non-determinism, which is a really interesting concept. But anyway, the point being, if you have a bounded queue and you receive some messages and you behave in response to one of those messages and you try and send yourself a message and the queue is full, you could, if you were to send a message to someone else and their queue is full, you could wait. But if you try and send a message to yourself and the queue is full, what do? There's nowhere to go from there. You're stuck. You've deadlocked. Because you can neither select another message from the queue and handle it because you haven't finished handling your first message, nor can you deliver this message. So there are all kinds of ways you can hack around that. You can keep two queues. You could say, well, I'm going to have a separate linked list of messages that I send myself. But all you're going to do is end up backing yourself into the same corner, which is to say that at some point you're going to need an unbounded queue for being able to send to yourself. And it turns out you can expand this and get rid of the self-send messages just by considering some cycle of actors that send each other messages, where it's possible for actor A to be sending a message to actor B while actor B is sending a message to actor A. Both queues are full because they've both been receiving messages from actor C, and that's it. Nothing can proceed. And you need a way out. So Pony uses unbounded queues. There's some other lower level stuff, like because actors in Pony have an overhead of only 256 bytes, we don't want to have a bounded queue that adds to that overhead. If we had a queue of 64,000 messages, well, that's 256,000 bytes given an 8-byte pointer. Wait, I've probably done that wrong, actually. That's 512,000 bytes, excuse me. But that's overhead that we don't want to pay per actor, right? That's a huge amount of memory. And it's very normal for a Pony program to have a couple 100,000 actors simultaneously. So we just can't afford the memory. But it does lead to the back pressure problem, of course.
Right, so do you have a generalized mechanism for back pressure within the runtime? Or
not yet. So this is a very interesting thing. This is something that Sean Allen has been working on quite a bit. He's one of the Pony core contributors. We think we're getting closer to generalized back pressure. We've had a couple of implementations that seem to apply back pressure the way we want it to, but the performance cost is too high. It's still lower than a bounded queue, but it's too high for us. And we've had some implementations where the performance cost is almost nothing, but the back pressure it applies is basically useless. So eventually, hopefully, we'll settle into something more useful. In the meantime, what we've done is applied a system of muting and unmuting on input actors, the most important of which are the network input actors. I don't mean that in the long run they're the most important, but in the sense that right now people are mostly using Pony for server-side processing, and it means that they're event-driven, and those events are generally delivered on the network. So far, TCP and UDP data coming in seems to be the thing that we want to provide back pressure to. Particularly, it's pretty easy with UDP because we can drop messages and everything's okay. But with TCP, being able to really provide TCP back pressure to the source, wherever that source process is. So there's a muting and unmuting feature now that the programmer can use to supply that back pressure. And the result has been some really interesting high-speed applications, particularly out of a company called Sendence in New York that's building event stream processing software.
Yes, in fact, Sean spoke at KubeCon New York a couple of weeks ago, so we have him on tape talking about his Pony experience coming up any minute.
Hey, fantastic. That's good synergy right there. So, so being able to provide that back pressure is great. The fact that we can do it is good, but we don't like the model right now. We really don't like programmers having to manually fiddle with TCP mute and unmute to try and get the behavior they want. So generalized back pressure is on the way. And of course, if anyone has any ideas, please get in touch, get involved. This is a project. Well, nearly every project in Pony would benefit from many of your listeners' expertise, but this one I suspect in particular.
Cool. So it's obviously still a very young language. You're still building out lots of things. I'm curious to know how some of these ideas have worked out in practice. So have you had the opportunity to run it on, say, a very large multi-core machine? I don't know what a very large multi-core machine would be now. 4,000 cores, something like that would qualify as large, I guess. Have you had those experiences?
Yeah, I mean, the SDI boxes get that big. Nobody else gets that big yet, except the SDI boxes. We have run it on a 4,096 core SDI box, funnily enough, at Imperial. And it coped pretty well. Unfortunately, dealing with the queuing systems that tend to get used on those boxes because they're designed for HPC workloads means that we were only able to run very short tests. And I'm not entirely convinced that the operating system was giving us all of its cores, but we think it was. Yeah, and it performed all right. I think more interestingly, it seems to perform extremely well on your sort of 64-core boxes with, half a terabyte of memory arranged in a NUMA configuration, and it does really well there, which I'm really pleased about. That seems to be the sort of top-end target right now. Your sort of very large Amazon EC2, your very large Azure instance, biggest things I've seen in bank data centers run about that big. So that's pretty good. On the other hand, we've also run it on a Raspberry Pi quite effectively, and that's fun too.
So do you get a reasonably linear performance as the number of cores goes up, at least to the kind of 64 core range?
So far, as long as the program isn't written to require coordination, we're getting strictly linear performance, yeah.
Yeah, it's astonishing, I think. And is that that's presumably partly down to the fact that you can share mutable data?
It is, yeah. As much as I want to make sure that people understand that they should use immutable data whenever possible, the ability to pass mutable data along in a sort of a pipeline fashion where the first actor allocates something, manipulates it, builds some complex graph, but it's an isolated graph and can be passed to the next actor for mutation, which can be passed to the next actor for mutation, turns out to be a really, really useful pattern. Another interestingly useful pattern is for actors to hold isolated data and to actually, rather than send data around, you send code around. So an actor might send a lambda to another actor to run over the state it holds. And that lambda might involve asking that actor to then give up that state and hand it to a different actor entirely. So there's some really interesting work patterns that can emerge.
Does the kind of algorithms that you implement in an actor model language, does that influence performance as well? I'm assuming that you would, because you would end up designing things in a very specific way because of working with actors.
Yeah, I agree. The most common thing that I see that is difficult for people to start thinking about is the tendency to have one big hash table. So there's one big hash table, which is the core repository of knowledge, and we're all going to go and lock that hash table and read from it, or lock that hash table and mutate it, or maybe there's using a locked free hash table, but that carries its own costs, and that just doesn't work in an actor model language because that's the point of contention. It means that you start getting this bottleneck where everybody is sending messages to this actor that holds that state to ask it to mutate it or query it and give an answer and respond. And it creates this bottleneck where that actor runs on a single core. And that's not great. You've introduced your own coordination mechanism of sort of bidirectional messaging on top of that actor. But it's not that hard to overcome that bottleneck, it turns out. Building a system that is more about event stream processing in the sense of sort of complex event processing is sort of the way to go with actors, where you sort of turn the database on its head. Instead of saying, I have data and I want to flow my queries through them, you say, I have queries and I want to flow my data through it, through this collection of queries or operations. And then you just get rid of these bottlenecks and you can start really segmenting stuff and really driving to that linear performance in the application as well, not just in our crazy micro benchmarks.
And that's really interesting. I mean, you mentioned that you've worked in investment banking, and obviously that Sean Allen is working on financial systems as well. And you've got that finance systems are essentially event stream processors a lot of the time.
We don't write code, we don't write software, we write time-dependent event stream processors.
Right. So presumably when you were thinking about the language design and kind of scratching your itch at the investment banking house, that was what you were thinking of, was it?
Funnily enough, the first thing I was thinking about was flight simulators. I used to write flight simulators, I'd say for a living, except it didn't work out that well. And it turns out what we were writing was pretty complex. We were doing real-time finite element analysis and some sort of very cheaty, hacky computational fluid dynamics to model aircraft in a very thorough way. Not to the level where you'd want to give this to Boeing, but absolutely in the level where you'd want to give this to some other interesting sorts of people. That turned out to need event stream processing, although I didn't know it at the time. And it turned out to need distributed event stream processing. And really it was about having feedback loops in physical models, that you wanted time-delayed feedback loops in physical models. And it turns out that's asynchronous message passing. And so my original goal was to write a language that would make writing my flight simulator a lot nicer. That's not at all what this turns out to have been, but that sort of was the original goal. But yeah, it turns out that style of asynchronous message passing is an incredibly good fit for financial systems, a staggeringly good fit.
So we've talked quite a lot about what Pony is kind of good for, as it were. Are there places where you wouldn't use it?
Absolutely. First of all, it's not a scripting language. If you have some small project and you want to do some work fast, there are many other lovely languages that you can use. I personally love F# for that. It's F# using FSX files. It's awesome. The other thing that it's not yet good for, and I don't know if it ever will be, is it's not really used for client-side programming. No one in the community has gone out and produced windowing system bindings, or there was a little bit of work on DirectX and OpenGL, but I'm not sure how far that's got. On the other hand, there is an entire roguelike written in Pony that's called Acolyte that's ridiculously fun. So you can do a little bit. It's got a curses interface. John Mumm wrote Acolyte. It's very good. So right now, client-side programming is not really where Pony excels. I think if you have a problem that is in no way parallel, then Pony is maybe not for you. You're not going to be using actors, really. You're not really going to be using a data race-free type system because you didn't have concurrency, message passing, and data race issues. So maybe you prefer a language that didn't impose that type system burden on you, given that you're not really benefiting from it. My personal bent is there are very few problems that aren't actually concurrent, but I'm willing to believe that someone has one.
And the Pony guidelines, the guidelines on the Pony Lang site, talk about, or at least imply that Pony as a language is quite strongly opinionated. So you talk about having restricted syntax, you talk about providing a clear way of doing things rather than catering to every programmer's prejudices. Is that, in general, there's a sort of classic argument about being opinionated versus not being opinionated. Where are you on that debate? Does Pony reflect your kind of view on that? I'm assuming it does, but...
Funnily enough, I would go with, we make a good show of being opinionated, but the truth is we're not. And I think I kind of like that space where the community tries to settle on ways of doing things, and we've got a really nice RFC process. It's nice because we stole it from Rust, who have a fantastic RFC process, and ours is just an imitation of theirs. So in the sense that everybody gets to contribute to the language, and the language really does evolve. For example, I didn't think we were going to have heavy usage of persistent data structures, but Theo Butler wrote a really nice persistent data structures package for Pony, and it turns out we use them all over the place. That's interesting. That was a big change in the way that we thought about things. In terms of, there is maybe a tendency to say that the language shouldn't provide two ways of doing things, but it's fine for different packages to provide two different ways of doing things. In fact, in a funny way, it's why we're a little bit slow to move things into the standard library, is that we'd love to get to the point where we have a good enough package management system where we had good enough discovery, and we're not there yet. We have a package manager called Stable that doesn't really do discovery the way we'd like it to yet. That's Joe McElvain's package manager that's very good, but just maybe not there yet. On that case, I use it, I love it, he wants to improve it. So there you go. So that we could have a lot of competition amongst packages and say it's fine to start a new package to do that thing because maybe you've got a different approach, you've got a different API, you different constraints. I think there's probably 2 or 3 different parsing expression grammar packages now, including one of mine. That's great. None of them are in the standard library yet. Maybe they will be, but it's great to have different approaches. At the language level, though, are we opinionated? I think maybe then at the language level, we're a little more opinionated. I think the type system kind of encourages that. On the other hand, one of the things that we're opinionated about is structural typing, which sometimes people find very surprising in a very strongly statically typed language with data race freedom like Pony. But our type system is about as constraining as Go or Python in terms of how you can use it. In other words, if you have a Pony type and it kind of behaves like this structural interface, it's got the same calls, looks like a duck, quacks like a duck, it's a duck. And that gives you a lot of freedom when you're building APIs. We also have a strong nominal type system that you can use as well if you want to use traits instead of interfaces because you want to force naming. That's okay. We mix them. But that structural type system means that there's maybe a little bit more fluidity in approach than you might expect.
Very interesting. I could chat to you for hours. I would love to, but we should probably wrap it up there. Thank you very much indeed for making the time. Really appreciate it.
Thank you very much for having me. I appreciate it.